This is the hardware course. This is going to be about opening up your PC or opening up your phone, looking at what's inside of it, and understanding how your code is actually being executed by the hardware. So it's the study of hardware at various levels of hierarchy. It's everything from the transistor level up to building of computers by slotting cards together, in some cases building computers out of other computers, up to the levels of clusters and cloud computing, and so on. Okay, so I'll just let you know a little bit about myself. I'm Charles. I studied at Cambridge, in Edinburgh, and Oxford. I really work in robotics and automation. I've also worked as a hedge fund trader. I was a quant, doing things with financial options and derivatives and data. I've worked as a data science consultant. My research here is largely on agricultural robotics. This is a big thing here in Lincoln. This is one of our robots called the IBEX system. I also work on self-driving cars. We have a vehicle in a lab a couple of doors down the corridor you might see driving around. And I work in data science, especially related to those two areas. I'm not a professional computer architect. Not many people are nowadays, but I'm a user of architecture. All of these applications require quite interesting, novel architectures. Okay, if you're doing anything in AI nowadays, you're using some kind of parallel computing, maybe GPU architectures or cluster computing architectures. If you're doing anything in robotics, you're using embedded architectures. These are computers that are designed to sit on a robot. You can't just plug them into the mains power. You can't just plug them into the wired network. You have to think a lot more about power requirements, radio communications requirements, that sort of thing. Data science is becoming very distributed, very parallel again. So I'll give you some special emphasis on those areas. Not many people work in computer architecture nowadays. Maybe a few of you will. Maybe in a class like this, maybe one or two of you will go and become maybe chip designers, or you might be involved with using architecture at low levels of software, things like writing compilers or writing operating systems where you're working with the machine. Most of you are not going to do that. Most of you are going to be users of computers, but by having some understanding of what's happening under the hood, you can become a better programmer in whatever field you work in. You can become a better games developer if you know how the hardware is really working so that you can hot rod it. Okay? You can become a better IT consultant if you know what all the numbers mean on hardware specifications, so when you get given a £1 million budget to buy hardware, you actually know what it is you're buying, what's going on under the hood. So I'm going to teach you this primarily from a user's point of view rather than from a learning to be a computer architect point of view. If you want to be a computer architect, it's a good foundation, but you'd probably go on and take other courses in chip design and so on beyond this. Primarily, this is what's inside the computer for people who are working outside of it. Okay? So, what is computer architecture? What's it about? It's fundamentally about the principles underlying computer hardware at all levels of hierarchy. So the letters ARCH, ARC, they mean control or power or being the master of something. If you're an arch enemy or an archangel, then you're a very big important enemy, a big important angel. So architecture means the overall big structure of design. How do you view the structure of a whole computer in this case? When we talk about hierarchy, the word hierarchy also has the letters ARCH in it. Hierarchy. This is coming from the same root, and a hierarchy means we're going to build big complicated things out of layers of smaller things, recursively. So the whole structure and the whole study of computer architecture is about the study of hierarchies. It's about, in this module, it will be mostly starting from the bottom. We're going to start with what is a transistor, what is a silicon chip, what is silicon. We build larger structures out of that. We build logic gates. We build simple machines, like devices for adding numbers together, for representing data. We put those together to make larger structures like a computer processor or a memory chip, and we put those chips together to make a system. So the whole structure of this module and the whole structure of the subject is about hierarchy, and it's the same arc you get in hierarchy and architecture. They're very very linked ideas. So typically we'll be studying some individual component level at a time. At any level of this hierarchy, we'll assume we have the previous levels available to us. So we might have looked at transistors, and we're going to look at how you put a bunch of transistors together to make a logic gate. Then we'll look at how you put a bunch of logic gates together to make an adding machine. Then we'll look at how you put adding machines and other things together to make a processor, and so on. I'm going to emphasize the historical trajectory of the subject a little more than most presentations. We'll be looking at devices from ancient Greece, from the Renaissance, from the Second World War. Is everyone familiar with the code-breaking work of World War II? It was a famous part of computing history. We look at some steampunk systems from the era of Charles Babbage. The reason we do this is to understand the direction that history is progressing. If you can see what's known as the arc of history, you can see the general trends over not just decades, but over centuries. It gives you an idea where all of this has come from, where it's going, and most importantly, where it is likely to go in the future. If you understand the past, you can avoid repeating the errors made in it. It's often said those who don't study history are condemned to repeat it, but you can see where it's pointing. It gives you some idea where the future of this is going to go. So at the end of the module, we'll look at some of the more research-based ideas for future architectures. So this can involve things like neural computing, architectures based on the human brain, DNA computing based on biology, quantum computing based on very counterintuitive theories of quantum mechanics. By understanding this trajectory, you can be prepared not just for what's happening now when you graduate, but for your whole career. What's architecture going to be like in 20 years' time? You need to be ready to adapt to those kinds of computers if they come online. Okay, so why do we study this? As I said, probably one or two of you might actually work in architecture. You might go on and get a job at, say, ARM in Cambridge in the UK. That's one of the main places where architects work here. Or you might go to Silicon Valley and work for Intel or AMD. But the real purpose as users is that by knowing the hardware, you will become a better programmer, a better network admin, a better IT consultant. You'll have some idea what's going on under the hood. It's like if you drive a car and you spend some time studying how car engines work, that can make you a better driver because you know how to operate the machine more effectively. So in particular, this knowledge will enable you to write code that is faster. Historically, that's been most programmers' objectives, especially for games programmers or other people who really want to hot rod machines if you're doing physical simulations or big data on very large computer systems. Increasingly, though, the emphasis is moving on to other objectives now, like lower power computing and lower memory computing. This is important now because more computing is done on devices like this that you carry in your pocket. This is a physically small computer. It is a computer, it's a real computer, but it's very small, it's very reliant on a small battery, it's very reliant on fitting the memory chips in there, and increasingly everyone is interested in optimizing to those kinds of requirements now. And these are requirements that are implemented at the level of architecture. Security is also a relevant use case for architecture. It's often the case that the system can seem secure at some level. If your view of a house is of macroscopic objects like doors and windows, and your theory of doors is that they're solid and secure, then it's very difficult to break into a house. But if you change your view of what a door is, instead of viewing it as a single macroscopic object, and you view it as a collection of smaller objects, like panels of wood and locks and the barrels in the lock, the levers in the lock. When you start thinking at that level, it gives you much more opportunity to crack the system. You can see where the flaws are and how to bust into them. So if anyone was following the news last year, there's been a whole series of security incidents based around these Meltdown and Spectre bugs. These are bugs that exist at the level of architecture. They're bugs in the CPU itself, at the level of silicon. As far as we know, they've not been exploited in the wild. There's been a lot of theorizing about how they could be exploited. All the kernels are getting patched now to defend against them. Ultimately, they're going to have to be fixed at the level of hardware. But by understanding what's going on at this level, maybe some of you will get into offensive computer cracking, probably more of you will get into defending against those kinds of attacks, but it makes you aware of what's happening under the hood, where bad things can happen. Okay? And overall, by following this arc of history, it's not just about studying the past, it's about seeing where this is all pointing that enables you to predict or even create the future. Okay. Here's a quick overview of the course. This is the introduction. So we'll start next week by looking at history and future, the arc of history. We'll spend some time looking at data representation. This is about how you represent everything from numbers to images, sounds, movies, using zeros and ones at the level of electronics. We look at digital logic. So this is about building systems from logic gates and and OR gates, not gates. Then we get into the meat of the subject. If you only come to one lecture in the whole course, you want to come to lecture 5. This is how the CPU works. The CPU is the center of computer architecture. It's the center of your computer. That's the core of the subject. Everything else feeds into the CPU. We're either implementing a CPU or we're building stuff that connects to a CPU. So lecture 5 is the heart and soul of it all. Lecture 6 is more advanced CPU concepts. We'll look at the difference between a classical CPU and a modern CPU, which has lots of WYSI optimizations. We'll look at some of how those optimizations work. Then we'll go outside the CPU. We'll start by looking at memory. We'll look at I/O, input-output. This is connecting the CPU to other devices in the outside world. And how the connections, the buses between those entities are set up. And then we look at some applications. We'll look at embedded systems. These are the kind of systems that appear in my robots, systems that are just designed to run out in the physical world. We'll look at parallel systems, like the architectures that are used in my data science work, in some of my AI work, in cloud computing. Then we have computer performance. This is about how you measure numerically how well an architecture is doing. This is important if you're buying computers. You need to know what the numbers mean in the metric. Specifically there, we'll look at some current commercial systems. We'll look at the history of the architectures that you have on your desk today. And then for fun, really, we'll look at some potential future developments in the last lecture. This might involve crazy things: DNA computing, neural computing, quantum computing. Okay? Then you get a reading week at the end before the second in-class test. So talking of reading, you guys really have to read, okay? If you don't read at least one of these books, cover to cover, you will not pass the module. I expect you to read an entire book on this module at the rate of about 1 chapter per week. If you don't read your chapter per week, I expect you to fail. These are big books. Architecture is a big subject. They're all in the library, and at least one of them is also here as an e-book now, so everyone has access to the e-book. You might want to invest in buying one of the books. They're good things to have around throughout your whole 40-year career in computing after you graduate. But you really have to read. You come to university to read your subject. You read for a degree. You have to read. If you only come to the lectures, you're only getting a quarter of the whole content. The real content is in the book. You have to read the book every week. Okay? There's 3 particularly recommended books. Nolan Lobo, the top one, is probably the simplest one. It's very nicely written, very easy to read. You can read it in the bed or in the bath, which I do regularly. Very nicely taught. The other 2 are more authoritative and scholarly. If you want to look up fine technical details, you probably go to the other 2. So take Nolan Lobo for your kind of teaching approach, and then take these other 2 for the serious fact. Tannenbaum, by the way. Anyone heard of Andrew Tannenbaum? Okay. Anyone heard of Linux? Anyone heard of Minix? Yeah? Okay. So if you get into free software and the open source movement, Linux is based on a previous system called Minix, and Tannenbaum is the author of Linux. So he really knows his stuff. So this is a very authoritative textbook because ideas from there have made it into the systems that we use every day now. So sometimes I'll give you extra reading in the lectures. If I put a slide at the end of each lecture, it will sometimes say recommended reading or required reading. If it's required, then it's examinable, basically. If it's recommended, then it might help. So in particular, in the history of computing lecture, I'm going to give you a big academic paper about a historical architecture that you really do need to read to get those details. Okay, so this is optional. Extracurricular activities. You don't have to do this, but I would very strongly recommend, as much as I possibly can, that you will get much more out of this if you are actually doing it and applying it to your own interests and your own projects in your own time. Okay? In the workshops, we'll cover the absolute basic minimum that you need to know about the subject. But to really get into computer architecture, you should be doing it. Okay? So some of this has to take place at the hardware level, which we understand is a little difficult and expensive, but there are things you can do at the software level. So if you guys are running GNU Linux stuff, if you're able to work with assembly language, there are free software assemblers and compilers. You can go into those programs and see how they actually work. You know, try and figure out how your computer works. What is the assembly language that you can give to the processor? How's the memory set up? How does it link to the operating system, and so on? There are simulators and emulator tools out there. These are programs which give you a virtual environment of some other computer. You can get simulators and emulators of historical architectures, you know, things from World War II, things from the 1980s. Retro gaming is relevant here. What was the architecture of the machines used in the 1980s, say? Anyone know the difference between a simulator and an emulator, by the way? Okay. I think it's the other way around. I think a simulator is simulating the actual processes by which your commands are implemented, whereas an emulator will give you the interface, but it might get implemented in a different way. So some simulators will go right down. There are some simulators that are simulating the actual speed of electricity flowing down the copper wires in a circuit, that kind of thing, whereas an emulator will just give you the same instruction set. So for some of the applications, that distinction is important. If you're really studying the inside of the computer, then you need a simulator. But if you want to act as a user of a World War II machine or something, then an emulator is going to be fine for your purpose. Again, these used to be quite hard to obtain. Now they're very easy to obtain. Lots of great free software out there you can download in a couple of minutes and run on your Linux box at home. If you're interested in security, not just cracking your neighbor's Wi-Fi, but if you want to mess around, try and break into existing programs, as I said, there's a lot of things you can do at this level. If you understand the level of assembly language and machine code, the classic way of cracking proprietary software is you take the executable file, you reverse engineer it, you understand what each of the instructions in that executable file is doing to your CPU, and you can find the locations where the security checks are getting done. Maybe you have a music program that requires a dongle to be plugged in or something. You find the function at that language, at that level of assembly language, machine code, and you just bypass the function where it's doing its security checks. So this is the level you work for classic cracking of proprietary software, or for trying to defend against such attacks if you're that way inclined. If you're interested in this system software level, if you're interested in how your kernel works, again, this links to your operating systems course. If you're interested in how compilers work, you will see these concepts are used at that level. There's not many people who program in assembly language nowadays, but it's the people at this level who are doing that. Actually, the main place you'll see it is in the bootloader. If you fire up your Linux box and it's running grub, it's the first thing you see on the screen before the desktop comes in. There's a lot of code there running at assembly level because you haven't loaded the operating system yet. Most of the programming we do nowadays is sitting on top of an operating system, but if you're writing the program that loads the operating system, it all looks a lot more like a 1980s 8-bit micro, the level you're programming at. You have to work with the machine itself. Retro video games are educational. If you try and go a little beyond just playing them, try to understand what they're doing inside. So I grew up in the 1980s. I spent a lot of my childhood busting into 8-bit games and trying to change the number of lives I had, trying to get infinite lives, mess around with the rules, put silly messages in there. We used to have tools that would show us a map of the whole computer's memory on the BBC Micro. You could press a special key and it would just show you the layout of memory. You could go in there and poke stuff into memory, and you could try and find out where the variable was that was storing how many lives you had and just put it back up to 3 every time. So if you try and get into things at that level, again, this is much easier to do now because there are these great simulation and emulation packages out there. There's one called BBEM for the BBC Micro that will let you do exactly that, just like in the good old days. The other application of this stuff today is in these embedded systems. Again, it's a place where you might code without an operating system. If you're writing a program to run on a small chip on a circuit board that's going to go in a robot, or you want to do things with the Internet of Things, maybe you want to turn your fridge into a smart fridge that detects how much milk you've got and automatically orders it from Tesco. Or if you want to track your books around the house or put a thing on your car keys. What's the other one we had? A plant watering device. You can build an embedded system to monitor the moisture in your houseplants and pour water on them. Play around with Arduinos and things. You'll see this level of thinking in those kinds of systems. If you want to get really into this stuff, it's actually possible to design and make your own chips now. You can, if you look at the structure of a system called RISC-V, this is a fully open source chip architecture that anyone can download. You can burn these things onto your own chips using a system called FPGA, which we'll look at later. That's the more advanced stuff, but the last couple of years have been the first time that anyone can do their own chip design for a couple of £100 now. Okay, so I'd really recommend you get into that stuff. Not everyone's going to do that, but if you like this stuff, go and actually do it and apply it. By way of introduction to the subject itself, then, to study the architecture of computers, we need to understand what a computer is, first of all. I want to try and convince you that's a somewhat less trivial question than you might think. What is a computer? What is it really for? What makes this a computer but not my calculator? What's the difference between those systems? We'll talk about the components of a typical computer. Again, this subject is about hierarchies. We're not going to look at every level. We'll start with the level of the human world, the parts of a computer you can see as a way into the subject. And then in the rest of the module, we're going to break that down and build it up in other ways. And then I'll give you a more detailed overview of everything we're going to cover in the module. So let's take this question, what is a computer? Okay. Probably most of you think you know what a computer is. You're studying them for your degree. You think it's the thing on your desk or the thing in your pocket or maybe the thing you plug into your TV to play games on. Maybe it is your TV. Is your TV a computer? Okay. Anything that can process information? Yeah? Any more? Something that can run arbitrary codes. Yeah? Something that can store information. Okay, so we've got ideas of information, processing, storage. Okay. So let's look at a few maybe problematic examples. So does a computer have to be electrical? No. Okay. So here's an example of a water-based computer. So this guy isn't just hot rodding his processor to play video games with overclocking. He's actually built the computer out of water here. This is the MONIAC system. It's designed to simulate the economy. They've taken a bunch of differential equations about how money flows around in the economy, and they've turned them into physical calculations using water. So the water represents the money, and there are tanks here representing things like government funds and savings and investment. And you can, for example, try and calculate the effect of a change in the interest rate. If you turn a valve to increase the interest rate, you'll see all the water move around, And you'll see the effects of that on unemployment and investment and so on, according to a particular theory of economics enshrined in the model. So is this a computer? Would it meet your 3 definitions? Yeah? Maybe not yours. Yeah? So if we moved around the components, we could effectively reprogram this to calculate an arbitrary program. Would it still be the same computer if we did that, or would it be a different computer? Yeah?
If you define the code as a series of rules it has to follow, then
Mm-hmm. Okay, so if the physical world is already computing and we're just exploiting that, then why is this a computer but the chair next to him is not a computer? Because the chair is following the same laws of physics as the water machine. Doesn't process information, yeah? Okay. How about if we took that chair and we made it represent information? If I had 10 of those chairs, and if you're sitting on a chair, I'm going to treat that as a 1, and if you're standing next to the chair, I'll treat that as a 0, and we'll get you to do adding by standing up and sitting down. Is the chair a computer then? Yeah? Not just the chair and the people, or the system, the complete system. Yeah? A collection of objects, yeah? Okay, how about if I took the chairs and the people and they're doing exactly the same process of standing up and sitting down, but they're not actually representing numbers. I'm not doing it to make them add something. I'm just getting them to stand up and sit down according to some rules. Yeah? So maybe it depends on the intent. If someone's trying to get information out of it, okay? So we could have this same water computer sitting there, computing away, and if there's someone in the room who knows that the water is meant to represent money and they understand the mapping, then it's doing computation, right? But if there's no one in the room, or everyone who understood how the computer was intended to work, if all those people have died and the computer's just sitting there computing, but no one knows what it means, is that still information? Is that still computing? Okay. So maybe it depends on the difference between data and information. Maybe the thing can be processing data, but it's only information if somebody knows what the data means, what it represents. Okay? Something that changes an input to an output. But what is an input and an output? Yeah, right. So again, if I'm using you guys as a standing up and sitting down chair computer, someone's got to decide what the input and the output is. You know, I've got to decide there's a coding of people standing up and sitting down as numbers somehow. Okay. How about this one then? Anyone seen this before? This is a 1980s theoretical model of computing with billiard balls. So what we have here, this is part of the whole computer. It's made out of gates. They're equivalent to logic gates and and or and not gates from electronics. Each gate is implemented as a little physical system. It has 2 inputs, which are billiard balls. Okay? And you throw the billiard balls in. If there's a ball, it's a 1, and if there's no ball, it's a 0. So you can build something like an AND gate like this. If two billiard balls come in here, they will collide. That affects their trajectories, and it means that one of them will come out this way instead of coming out that way. Okay? So you can create an AND gate by chucking the billiard balls together, seeing which way they go. Was there a collision or not a collision? That gives you a 0 or 1 coming out, and then you can build a whole processor based on that. So again, this is a non-electronic computer. What's interesting about this system is it's actually intended as a model of energy usage in computers. This has become important now. When you run your phone, it gets hot. Why does it get hot? Okay, it's using electricity. Now, the laws of physics say that energy is conserved, right? If I built my phone from these gates, you'd see there are 2 balls going in. They've both got momentum and kinetic energy, and they both have the same momentum and kinetic energy when they come out. Heat, yeah. Okay, so what is heat? Yeah, heat is any energy that is being thrown away. It's energy that's being wasted. Technically, it's energy that you don't know where it is. It's energy that you have lost track of where it is. Now, what's interesting about these gates is that an AND gate conventionally has only one output, and it has two inputs. If you build a conventional electronic AND gate, you're putting in energy from two directions, and you're only getting energy out in one direction. And this is where the heat comes from. It's because you've thrown away 1 billiard ball's worth of energy. Okay? In the billiard ball model, you have to keep track of where the other billiard ball is. If you can catch that billiard ball coming out the other end, you can build a computer with actually arbitrary low energy consumption. The amount of energy you consume will depend on the time it takes to run the thing. If you had a computer that ran infinitely slowly, it would take 0 energy. You can trade off the speed of the machine with the heat output. So it's by studying architectures like this, which have nothing to do with the computer on your desk today, but by studying a system like this, a theoretical architecture, we can get an idea. This idea then is that if we could build silicon AND gates that track that output, if we could catch that output, we could get the energy back out of it, and instead of making your phone hot, we could make it go around again and do more computational work with it. This is also really important in quantum computing. The other property of these gates is that if you know the outputs, if you watch where the balls come out, you can reconstruct exactly what went in. So a regular AND gate, if I tell you the output was 0, you don't know what the inputs were, because you can get that output in 3 different ways. Okay? With this gate, if the output is 0, you can also look at the state of the other billiard ball coming out, and there's enough information in the output to reconstruct the input. That means you can run your computer backwards. You could, for example, easily build a reverse debugger that will just run your program backwards, which would be really useful for a whole bunch of things. In quantum computing, the physics turns out that everything must have that property. You can only build a quantum computer that has this reversible property, because it's a basic law of quantum mechanics. Okay, is this one a computer? Anyone seen this before? Okay, this was found in a shipwreck in the Mediterranean a few years ago. It's from about 100 BC. It's from the ancient Greeks. People argue about exactly which ancient Greek designed the thing. This is a clockwork device. It was used for computing the times of eclipses. So you can just see the outline of some of the wheels. This is a reconstruction of it. It's a very, very complex piece of clockwork. It's an interesting question why this branch of technology never went anywhere. They almost invented something like Babbage's difference engine by doing this. Nearly 2,000 years before Babbage. So here we have this property of representing information. So the position of some of these wheels represents the position of a star or a planet or the moon. Other wheels are just used in the computing itself. You could have turned the handle on it and it would have predicted what day the eclipses would come. So we're processing information, we're representing information. But can it run arbitrary programs like we had over here? Okay, so this, as it stands, this device is only for predicting eclipses. Again, we could make the same argument as the water computer. We could say if you took all these cogs and reconfigured them, you could make them into an arbitrary calculation of anything. But again, would it be the same computer, or would it be a different computer if you did that? Okay, so how about this one? This is Royal Air Force Operations Room. What we have here is the representation of information. The table is a map. The models are representing the position of aircraft. There are humans involved in pushing those things around. We could maybe automate the humans to push things around. But what we have here is, there's obviously data, there's the position of these models, there's information, because we're using the models to represent something out in the real world. There's processing, but there are humans involved in the processing. Okay. Storage. Yeah. Yeah. Okay. So maybe if everyone here was following a rule book that told them exactly how to move things, if they're behaving algorithmically, it would look more like a computer. But yeah, there's clearly a lot of actual human intelligence being used here in telling people where to place the model. If they were doing computing from a rule book, would it matter if those models were representing real planes, or if these guys were just playing a tabletop war game for fun? Okay? In the first case, the models are actually representing something. They're really information. But in the second case, where they're playing a game, is anything being represented there? Okay, good. So maybe the models are representing objects in a counterfactual world, right? There's a possible world where a war really is taking place like that, and the point of the game is to actually play that out in the possible world. So we see here that information doesn't have to represent something physical. It can represent maybe something counterfactual, maybe something logical, maybe just something in other people's heads. So there's some kind of representation, but it's not a straightforward link from the data to the physical world. Okay, is this a computer? This was the computing division in a company in the 1940s. So that there used to be a job title of computer. You could apply for a job as a computer, and you would sit at one of these desks and you would perform an algorithm. People would give you numbers and you'd do some arithmetic. Not mathematics, you do arithmetic on it. And you'd follow the rules and maybe type things out on a typewriter and give them to the next person. So in the start of World War II, at least, this is how a lot of the cryptography was done. It was just rows of people at desks being given cards of information. This was a very sexist time, so you can see, here's the programmer, the guy, and here's all the ladies working as computers at this time. This actually led to a lot of women becoming really good programmers when the modern computer age started, though, because it was a way in for women working in these roles, and they were the people closest to the algorithms. And so we're going to see a surprising number of women in the history of computing who've come through that route. It was always the guys who thought they were doing the important stuff, but it was the ladies who were really understanding the concept of the algorithms. So is this a computer? Yeah, so it depends on the definition here. So in terms of a modern definition about information processing and general program forming. Okay, good. So this was taken to extremes in a famous thought experiment by John Searle called Chinese Room. Anyone heard of this before? Okay. It takes that idea. It says, suppose you are locked in a room and you're given these books of rules. You're given books of the algorithms. And there's going to be an input, which is a place that sends you pieces of paper with symbols on them. There's an output, and you're going to post symbols on. And in the Chinese room experiment, all the symbols coming in and going out are in Mandarin Chinese. And we assume you do not speak Mandarin Chinese. But what you have is a huge rule book, which is defining the program for an AI system, and it's going to have a conversation with a real Chinese human on the outside. And you're going to pass something called the Turing test, which means you're trying to fool the person on the outside into thinking you're a real Chinese speaker. So you get these symbols in, you have no idea what they are. Chinese symbols especially are pretty meaningless for most English speakers. You look them up in the table, you maybe do some intermediate calculations on bits of paper, you get an output symbol, chuck it out there, and you're ordering food in a restaurant or discussing Eastern philosophy or poetry or anything. So this question was posed really in the philosophy of AI. It was about what it means for information to be represented, these ideas of the difference between data and information. Is this computation because no one in the room actually knows what's going on? In fact, take an extreme version of this where the person you're having a conversation with is doing the same thing. So we've got two English speakers locked in rooms, and they're both having a conversation in Chinese, and nobody understands the semantics of the conversation at all. So Searle used this as an argument against AI because he said you can build this system that looks as if it's doing computation, it looks as if it's representing information and semantics, but there's actually no one home. There's nothing actually being represented by anyone. So I'm not going to give you an answer to this. This has been argued about for 30 years in the philosophical literature, but it's one of these thought experiment tools that is used to try and drive a wedge between different notions of computing. Where does this difference between data and information have to be represented? Maybe your argument could be applied here. You're saying maybe there's no particular, there's no one at home representing this stuff, but there could be. Maybe there's a counterfactual world where someone could be there with it, or maybe the guy who devised the thought experiment has an understanding of it. So somebody somewhere has a semantics, but not necessarily the people in the room.
I mean, someone would understand semantics.
Yeah, someone designed it, yeah. So maybe there's a counterfactual world where that person is sitting in the room watching the conversation and they actually do understand what's going on.
Well, would it have to be counterfactual? I mean, someone's like, if there's two English speakers in different rooms that don't understand what they're saying, where are we doing the experiment?
Yeah, yeah. Good question. It's important when we discuss this idea of generality. I think when you design a computer, there is some notion that a computer has to be able to do a fixed category of tasks, otherwise it doesn't classify as a computer. So if the thing you've designed doesn't meet a definition of a computer, then you might annoy people who want to buy a computer and the thing you've made isn't one. Okay? Okay, how many of these are computers? This is your car. There are lots of chips in your computer. This is embedded computing, like I mentioned, these low power, low compute devices. There's everything from systems processing GPS to the thing that controls your DVD, things monitoring your tires. There's an entertainment system. Where do you draw the line? Is your anti-lock braking system a computer, or is it just a piece of electrical machinery? Yeah? So maybe the car itself isn't a computer, but maybe some of these devices are computers. But probably some of them are and some of them aren't, right? Yeah. Yeah. So there's an increasing trend in car electronics for everything to talk to each other now. Most of these devices are sitting on a network called a CAN bus, which is a total security nightmare because it turns out that a bug in your MP3 player can now be used to get control of the anti-lock braking system. That's a really bad architectural idea. So increasingly, these things are functioning more like a single system. But it's probably the case that some of these devices could meet your different requirements for computing. You know, can you take your digital radio and reprogram it to play Space Invaders? If you could do that, that would look more like a computer than one that's only functioning as a digital radio. Someone's probably done one, yeah. So a pretty good intermediate definition of a computer is anything you can reprogram to play Space Invaders, right? If you look at a device, ask that question. That will give you a good hint. An off-the-cuff intermediate definition of a computer is anything you can reprogram to play Space Invaders, okay? That's not a formal definition, that's kind of what I would use in this sort of situation. So probably, yeah, your mobile phone, maybe your digital radio, probably your multimedia system would meet that definition. Maybe things like your GPS processing maybe wouldn't. Maybe they're not so programmable. Maybe they have some firmware on. But it's tricky. It used to be the case that by computer we meant this thing on our desk, and it was very clear that was a computer and my car wasn't. And architecture is shifting now. It's blurring into all these other devices. So this is from Douglas Adams, right? This is the deep thought computer. Who's read Douglas Adams? Yeah. So the premise here is that the whole Earth was designed by some greater power as a computing device. Every process in the biosphere, in the geology, is actually representing something. So you have all these physical processes, like the water in the water computer, and the thing's been left here for 4 billion years to compute the meaning of life. And part of the joke is that people have forgotten what the question was, so the semantic content of the computation has been lost. So it very famously comes up with the answer. You probably all know what the answer is, but everyone's forgotten what the question was, and so again there's this question, was this actually a computation if nobody knows what was actually being represented? Yeah? Could the Earth really be considered as a computer if there was someone who had a mapping from its state into some kind of semantic representation? Okay, we'll take a break in a minute, but again, this is not the answer. This is not the formal definition. This is something I'm just offering. Dictionaries are written not to define words. They are written today to represent how words are being used by the people currently around them. So they reflect what other people are using as their definition. But according to the Oxford Dictionary, it has to be electronic, which seems very arguable. The electronic device able to store, manipulate, and communicate information. So I think that's actually all the key words you guys have shouted out already. So not data, but information. And the word information has this semantic connotation. So it can perform complex calculations, control or regulate other devices or machines. It's capable of receiving information and processing it. So it has to have some input and output as well. It can't just sit there computing in this definition. And it has to be reprogrammable. It has to have variable procedural instruction. So that doesn't have to be the formal definition. That's just what some arts graduates working for the Oxford Dictionary Company have come up with. Okay? So yeah, you've got to have one program versus any program. You've got to be able to run any program on a device to be a computer. So this is probably not a computer because this only runs the calculation. This is a computer because you can write Space Invaders for it. Probably some of these are and some aren't because you can write Space Invaders for some of them. You have this notion of data versus information. So data is just zeros and ones. It doesn't mean anything. Information is data that is about something. It has semantics. What does it mean to be about a thing, to be about something? You know, is a thing an object in the physical world? Is it an object in someone's head, in your phenomenal world? And what does it mean for aboutness to exist? What does it mean for data to somehow connect to this thing in the physical world or to someone's head? You know, is there a wire from the data into this real object or into your head, or is that relation sitting somewhere else? Somewhat philosophically, can computation exist if no one is around who understands it? This is the premise of Douglas Adams. There's a theory called pan-computationalism, that everything is a computer. You know, that could be the case if God created the world to compute something, but someone would have to have the semantics. Okay?